So this is the process that we follow. Then we did the XRT analysis. The figure illustrates that the X-ray diffraction pattern obtained of the Mg1 minus x Cx by 2 Fe2O4 sample, the observed diffraction pattern aligned closely in both diffraction peak positions and relative intensities with the reference to JCPDS card 221086. From that we matched it, and we did not see any extra peaks that are there other than the pure material. And specifically peaks are evident at approximately 30 degrees, 33.55 degrees, 82.47, 54 and 56 degrees for magnesium and cerium. These peaks correspond well to the crystallographic planes of spinal ferrites, especially 220, 311, 400, 422, and 333 and 440 mill indices. And we also, and by doping, we also see that there is a rightward shift in the XRD pattern, and that is due to the changes in the crystallite size, and that is because the cerium that we are doping on the ferrite side, magnesium side, the cerium has a lower Na radii than the magnesium. It is worth noting that the sharpness of these diffraction peaks can be attributed to the micrometer size crystallite within the sample. Furthermore, the XRD pattern affirms the presence of high single-phase cubic spinal structure, particularly evident in the case of pure MgFe2O4. This consistency in the pattern across all samples underscores the formation of a cubic single spinal phase. To determine the latest parameter,
Ashish Dubey,
Bragg's
please
law.
don't, Ashish Dubey, please don't read completely. You just tell me what exactly
Yeah.
the output of
Yes,
the
sir.
work.
Yes, sir. These are the we did the XRD analysis. So these are the lattice parameter and crystallite size that we found. So as you see that it is the crystallite size increases and then decreases with the doping. So with different doping of cerium, we see these are the different crystallite sizes that are changing. So these changing crystallized sizes will be very useful for our sensor application and sensor studies. Basically, we are preparing the material for their sensor applications. Then we did the Raman spectroscopy, and the Raman spectra that we did at room temperature, and we found that the MgPO4 spinel has a cubic structure belonging to space group FD3M, and the unit cells contain 66 atoms, and the smallest Brevich cell only contains 14 atoms. Now there are three Raman active modes that we found. Actually, four Raman active modes. Sorry, F2G, EG, F2G2, and A1G. So these are the Raman modes that we found, and the further analysis that we are doing, and we matched it with the standard spectra, Raman spectra of these materials, and we found that they are in very much in agreement with the standard plots of the standard journals. And these are the Raman spectra of the doped materials. Now, here different modes that we tried to explain why they are there. So A1G mode is due to symmetric stretching of the oxygen atoms along with metal oxide bonds in the tetrahedral coordination. EG is due to symmetric bending of oxygen with respect to the metal ion in AO4 unit, and it is caused by symmetric bending of oxygen.
Ashish Dubey, please make finish it. You have only 1 minute.
Yes, sir. So we are basically studying this material for their sample, their application as sensors for preparing sensor devices. Now, this material are very useful for sensor application because they have pores in them. So what happens when they put these materials in in an environment of a particular gas, like for let's say for a carbon dioxide or carbon monoxide. So this if the pores of the material are equal to the size of the ionic radii of the uh, carbon monoxide molecules, these molecules will actually will get absorbed on the surface of the material, and when it gets absorbed, the electrical resistivity of the material will change, and due to the change of electrical resistivity of the material, we can detect the gases.
Is done? Ashish Dubey, it is done? I'm not able to listen to your voice. Ashish Dubey, please speak. Ashish Dubey, what happened? Ashish Dubey, we are not able to hear you. Yeah, please stop sharing once, Ashish Dubey. Yeah, is Bhupendra Kumar is here?
Yes, sir.
Yeah, can you just start sharing your let me get back to Ashish Dubey back.
Okay,
Let
sir.
him okay. First start sharing your you're 019, right?
Sir, 0012.
Uh, yeah, 12, right. Yeah, you start sharing your
Sir, is my screen visible?
make it full screen better.
Okay. Right?
Yes, yes. So make it to just 5 minutes. You mostly concentrate on your what is the reason for selecting your work and what is the outcome of that.
Okay, okay, sir.
Yes.
So very warm welcome to all of you. My name is Bhupendra Kumar and I am here and I am a research scholar at IIT Roorkee. First of all, I want to express my gratitude for giving me a chance to discuss my work here. So the topic of my presentation is entitled as Josephson current across a double quantum dot Josephson junction and T-shaped configuration. So this is my content slide. I will start from the abstract of the work and then some background theory and then theoretical formulation, then the result part and the last some scope of the future work. So we
Thank you
stated
very
that.
much. I think mine is over.
Hello.
It's okay. I think Ashish Dubey was in.
Okay. Okay.
Yeah.
So this is the system I was studying. I have studied Josephson current in this system. Here we are seeing that quantum dot one is coupled with the superconducting leads, and the dot two, which is called side dot, is coupled with the quantum dot one. And basically we see the how this interdot tunneling. This T is the interdot tunneling, and this gamma is the dot lead coupling. We see the impact of interdot tunneling T and gamma in the Josephson current. So by using the Green's function equation of motion approach in this system. So let me just briefly explain the what are the quantum dot based Josephson junction. In starting, there are SIS junctions. If we replace this insulator from here, so we have quantum dot, or due to quantum confinement, there are discrete energy levels in quantum dot. So we can tune them, and the flow of current can be controlled. So in these quantum dot based Josephson junctions can be used in superconducting quantum bits and nanoelectric devices and squids and Cooper pair splitters. So what happens here? If we see this structure as this is some nanostructure and this is superconductor second. So one electron from the superconducting lead strikes to the dot, and it can back reflect as a hole. So it make a subgap state here. This is called Andrew bound state, and at the same time we are seeing a copper pair in the right lead. So this mechanism is called Andrew reduction mechanism, and transport of copper pair in these systems is explained by this in function, single particle retardation.
Next presentation will be yours. Bhupendra Kumar. Bhupendra Kumar.
Sir, can I present
Yeah.
my poster now?
Let me wait, Amma. Just wait for the
Function, this formula
presentation,
for
Bhupendra Kumar.
yes sir.
Bhupendra Kumar.
Yes sir.
Yeah, you just continue. Make it fast.
Okay, sir. So once we got the green function, this formula for disruption current or super current can be easily derived with the help of theory given by Caldias. So this is the result part. Here we see the effect of interdot tunneling T and dot lead coupling strength. So we see when T equal to 0, the electron directly T equal to 0 means there is no quantum dot 2, there is no side dot. So we get the highest peak, which is shown in the blue, color. So once we attach the second dot, so once we add the second dot, the disruption current starts decreasing. This is because now the electrons tends to tunnel into quantum dot 2 also. So with these structures, we can tune the disruption current in these systems or in the nanoelectric electronic devices. And second, we see the effect of dot lead coupling strength. So this is obvious. The disruption current will increase with the increment in dot lead coupling strength, which is shown in these four figures. So here I am concluding my work. For in future work, we can see the thermal transport in these systems and see the multi-terminal or multi-dot Josephson junctions for these properties. For thermal transport, we can try. Thank you, sir.
Okay. Any questions
Hello.
from the
Hello.
hello?
Yeah, sir, my name is actually Surya Reddy. My presentation was from 4:45 to 6:15, but I requested to reschedule it to this time.
Okay.
And
Can you just wait for 10 minutes? We'll have
sir,
some 2 or 3
sir,
presentations.
can I do it next, sir? Because I have to
Yeah.
attend some place.
Shivani RB is ready for that. After that, we can try.
Okay, sir. Thank you, sir.
Okay, right. Can Bhupendra
Sir,
Kumar, nice,
sir, my name is hello.
Yeah.
Yeah, sir, I'm Ashish Dubey. Sir, mine is over, or should I start
Okay,
again?
it is done. Don't worry.
It is done. Okay, okay, sir. Thank you, sir.
So,
Hello,
Shivani
sir.
RB.
Hello.
Shivani RB.
Hello, good afternoon, sir. I'm
Hello,
Mahidul
sir.
Khan. Hello, good afternoon,
Shivani RB
sir. I'm Mahidul Khan.
0013. Shivani RB 0013.
Sir, hello,
Hello.
hello.
Sir, mine is over. Bhupendra Kumar.
Hello.
Yeah, Bhupendra Kumar is done.
Okay, sir. Thank you.
Hello, sir. I'm Mohibul Khan. I want to present my work.
What is your number?
A10029.
A10029.
Yes, sir.
0029, I'll tell you, mostly after 2 presentations. We are
Okay,
going
sir.
in line with, there are some missing numbers. I'm going with the first missing numbers and then I'll go further. Please, Shivani Arvind,
Okay,
start
sir.
sharing your screen.
Okay, sir.
Start presenting your.
Hello.
Sir, is it visible? Can I start now?
Yeah, you can start. But the screen size is a little bigger. You just make it small. Okay, right. Okay, start. But make it
Yeah.
only 5 minutes.
Yeah, okay, sir. Good afternoon to everyone. Thank you for giving me an opportunity to present my work today in the form of a poster. My work is titled Comprehensive Examination of Ni at AgCl Nanoparticles, an Insight for Optoelectronic Applications. In this study, chemical reduction approach was used to successfully manufacture Ni at AgCl core shell nanoparticles with molar ratios of 1:1 and 4:1. The crystalline nature and face-centered cubic structure of these materials were confirmed by XRD investigation. Numerous characteristics, including crystallite size, dislocation density, lattice constants, volume of the unit cell, and lattice strain, were calculated using the Ferrer formula. And WH plot. The findings showed in that in comparison to sample B, which has a molar ratio of 4:1, sample A had a higher crystallite size and lower lattice strain. Both materials' spherical shapes were validated by morphological analysis using EDAX, which also revealed their chemical composition, indicating indirect band gap values of 2.53 electron volt and 2.45 electron volt. The UV absorption spectra of samples A and B revealed strong peaks at 237 nanometers and 239 nanometers respectively, which confirmed their semiconducting characteristics. For samples A and B, PL examination revealed emission wavelengths at 397 and 398 nanometers, falling in the UV zone. So this makes the my material, that is Ni at AgCl, an attractive candidate for photoelectronic applications. So you can see the images that I've attached here in my poster. That is all, sir.
Yeah, it's done. Okay.
Yes, yes, sir.
Yeah, I think I have seen the heading in the above the table, that is core shell nanoparticles, right?
Yes, sir.
So I think you have done core shell nanoparticle size using only XRD.
Actually, I've taken SEM also, sir. SEM and ADAX. So you can see the
Oh.
spherical structure here, and it conforms the core shell.
Yeah, I think there is one more experiment for this. What not only the TEM, dynamic light scattering method. I think is that right?
Dynamic scattering.
DLS,
DSR.
DLS.
Okay, okay, sir.
DLS.
DLS.
So this is the only suggestion. I think you can use of that experiment to confirm the same
Okay.
thing.
Yeah.
Okay. Thank
Okay.
you. Nice presentation, please.
Thank you, sir.
Next, Pratima, are you really ready now?
Yes, sir.
Yeah, you tell me. If you
Hello,
get
sir.
it, yeah. Pratima.
Hello, sir.
Yeah,
My screen.
you make it only 5 minutes, okay? It's very good now.
Sorry, is it visible?
Yes, yes.
voice.
Make it is only 5 minutes. Somebody is speaking outside.
Okay, sir. So, good afternoon, everyone. So, I'm Pratima from Research Academy of Technical Education, Noida. My topic of presentation is
Shivani
electrical
RB, please
enhancement.
mute your phone. Shivani RB. Shivani RB.
ठीक है सर,
Hello.
ठीक है सर. मैग्नीशियम का
Pratima, you can continue.
Okay. So, सर दूसरी आवाज नहीं आ रही है कोई. So my topic of
Asking the
presentation is electrical enhancement near plasmonic nitride and carbide based or at the rich shell and particle force engine. Outlines are introduction, motivation, electric potential near nano shell initiation, electric field and references. So introduction surface plasmon is the electromagnetic excitation propagating at metal or dielectric interface. When these oscillations are in resonance with the incident electric field or light, it results in enhanced electric field, enhanced emission, enhanced absorption, and enhanced energy transfer. Plasmonic nanoparticles are highly efficient at absorbing and scattering of the light by changing the shape, size, and surface coating. Optical performance of the one particle can be tuned. Conventional plasmonic nanoparticles are silver, gold, aluminium, copper, etc. And newly emerging plasmonic nanoparticles are titrides, oxides, carbide. Common geometries are spheres, spheroid, nanoshell, nanorod. Several theoretical models and tools are available to study and simulate the optical property of medical nanoparticles. Examples are MSC method, FDTD method, Mies scattering, etc. So motivation for this works is conventional coinage metals, example silver, gold are most widely used plasmonic materials adorned by low toxicity and high biocompatibility. Sulfidation occurs in silver, which results in damping of the surface plasmon resonance, and gold is accompanied by the low melting point and high plasmonic losses. So there is a need of good materials for as an alternative materials, refractive transition nitrides such as ZR and TI and characterized by high melting point, high biocompatibility, and high electron conductivity, etc. So here we use the formula for electric field enhancement near a plasmonic, near a nanoshell particle of core radius A and shell radius B, which is placed in uniform electric field along the z-axis. And dielectric constant is epsilon 1, epsilon m, and epsilon 2 of core, shell, and embedded medium respectively. So we have studied the effect of core and shell material for field enhancement. Here we have in figure A, we have taken the dielectric material as air, and shell material is our nitride and carbide material. Here from these
which to which? From here to here it is done. There are again still there are three more.
Sir, what? Hello. Hello.
You can continue. You can continue.
Okay. So here we can see that if we are using air, the resonance peak are in visible region, and if we are using Si3 and 4, the peak can shift towards infrared region. Next, we have studied the effect of size of core and shell. From these results, it is clear that as we increase the particle size, the field enhancement is also increasing, and peak shift also, resonance peak also shifts for different materials. Here we have shown for HFN and TIN nanoshell enhancement for different particles, and here for ZR and TAC nanoshell enhancement for different shell size with different electric medium. So summary is plasmonic behavior of nitride and carbide material is studied by varying parameters of size and materials. Field enhancement shows resonant behavior. Field enhancement is achieved in higher wavelength region in comparison to conventional gold material. Larger field enhancement achieved for larger particle size. And in comparison to spherical nanoparticle, larger field enhancement and better tunability is achieved in visible region using nanoshell structure. Electric field enhancement is an important factor in SERS, biomolecular sensor, etc. And nitride material can be used for better tunability purpose in different wavelength region in sensor applications. So these are the references. Thank you.
Yeah, so it's a nice presentation, but you made too late actually.
Sir, actually, now I'm presenting from phone. There is a
It's okay.
problem in laptop.
Can you just tell me what are the experimental methods to do the nanoshell structure or to study the nanoshell structure?
So there are different methods, but actually I'm doing the theoretical work, sir.
Yeah. Can you just name any experimental works? Any name, any brand, any two, three or names?
Sir, experimental works are basically nanoparticle XRD is SERS Raman scattering, sir. These are the experimental tools which deals with plasmonic nanoparticles.
Okay, right. You can leave now. Now
Okay,
the
thank
next
you very much, sir.
participant is Mohibul Khan.
Sir.
Hello.
Mohibul
Hello.
Khan.
Yes,
Hello.
sir. I am
Hello, sir.
present, sir.
Mohibul
Hello.
Sir,
Khan.
yes, I am present, sir.
Yeah, you start presenting.
Yes, sir. I am present, sir.
Right, you start presenting.
Hello.
Hello, sir.
Sir Surya Reddy garu, please
Good
just wait for one. After this presentation, you can do that.
Okay, sir. Thank you, sir.
Hello, good afternoon, everybody. Yeah, I am Mohibul Khan. Today I want to present my work, optical characterization of nickel dope zinc oxide thin film deposited by R sputtering technique. These are the outlines, introduction, application, experimental details, results, and conclusion. Introduction: zinc oxide is environmental safe N-type 2,6 chalcogenide semiconductor having band gap energy 31 volt at room temperature. Zinc oxide is a two types of crystal structure: hexagonal
Mohibul Khan,
urdite
your
and
screen.
cubic zinc
Mohibul
plate, and
Khan.
zinc oxide forces. Yes, sir.
Yeah, your screen is showing
Yes,
only
sir.
first page, not the pages are not moving forward. Your outline only. Screen presence is only outline. I think you went to introduction, I think.
Sir, sir, you can see.
No, it's still showing outline. Hello. First slide only. That is second slide, I think.
Okay, sir.
So please wait for 2 minutes. There is a one more presenter actually. A0010 Suraj Raghuvamshi.
Saroj Raghuvanshi.
Press, please. Saroj Raghuvamshi. Please share your screen.
Yes.
Please wait.
Okay,
Mohit.
sir. Is it visible, sir?
Yeah, it's coming. Let me see the screen. Now your name has come here. Please share your screen. The screen not shared. Yeah, I think it is getting. Yeah, make it full screen and confine it to only 5 minutes.
Okay, sir. Is it visible, sir?
Saroj. Yeah, it's visible. Saroj Raghuvamshi presenting now.
Yes. Namaskar, all of you. I'm Saroj Raghuvanshi, Assistant Professor in Sri Cloth Market Institute of Professional Studies. Today, I'm going to present my work entitled Effective Data and Disorder on the Structural and Magnetic Parameters of Zinc Ferrite, synthesized using the honey-mediated soil-gel autocombustion method. And the ferrites are a hard class of oxide with notable magnetic properties exhibiting ferromagnetism, which have been investigated and are used in various applications. General formula of the ferrite is MEO Fe2O3, where Me is the transition method. And this spinel structure composed with the 32 divalent oxygen rings outline and has the two sides which are known as tetrahedral and octahedral. So 64 tetrahedral, only tetrahedral sides are occupied by the divalent atoms, whereas 32 out of the 32 octahedral sides, 16 octahedral sides occupied by the trivalent atoms. It shows the large friction of anti sides, which increasing the cation distribution between the tetrahedral and octahedral side, influence the structural as well as magnetic properties of the ferrites. The available literature survey on the zinc ferrites provides the very much information about it, but still there is a systematic study of the synthesis method using the zinc synthesis as well as conventional flow is still lacking. That's why my basic objective is to study the effect of conventional fuel, that is the citric acid, and green fuel, that is the honey, on structural changes, cation distribution, and magnetic properties. Now, this is the process which I have used for synthesize the samples. And simple names are for in the dry gel forms, like using the citric acid is S1, and for using the green fuel, that is the honey, S2. Still annealing, the samples names are S3 and S4. Now the question is why there are various of methods are available to the synthesizing the material. So this soldier autocombustion method is the one of the most efficient method. Here we can make the ferrite material in moderate condition and control the parameters. Now XRD and VSM measurement were used to characterize the prepared samples. These are the pattern distribution. The prepared samples were measured using the Bartók method, and these are the following parameters which are very useful to study the structure of the crystal. Can be calculated by the Bartók method. Magnetic, using the magnetic measurement, I have calculated saturation, magnetization, and cohesivity. Now let us come to the result and discussion part. Here, this is the representative diagram of the XLD of one of these. It clearly represents the formation of nanoferrites with dry gel form as well as centering treatment after the head centering treatment. The observed changes in the grain size and the surface area clearly represent the role of chelating agent, and also the growth of the grain size shows the effect of heat treatment. Variation in the density is explaining the relocation of the ions within the spinel ferrite. The close agreement between the experimental lattice parameter and the theoretical lattice parameter confirms the cation distribution is close to the real distribution, and the migration of iron ion and zinc ion affect the crystal structure and also affect the relocation of cations, which in tune in the magnetic property of the material. Now, this cohesivity and saturation magnetization graph clearly indicates that the sample which is made by the using citric acid, which is the conventional fuel, gives the highest saturation magnetization value and lowest moderate cohesive value. Variation in the bond angle between the A and B side shows the distorted spinel ferrite structure, and the strengthening of the magnetic property we can get we can see due to the strengthening of the BB interaction by weakening of the AB and A interaction. Now finally summarize to my work. The synthesis of the ferrites using the in synthesis avoid the toxicity or reducing the toxicity, and this is very useful for further applications like hypothermia, which is very useful for the cancer treatment. Soldier autocombustion method is the eco-friendly method, which is also used for the mass production in the industry and reducing the cost of the sample. Now, thank you very much for your kind attention, and thank you very much for the organization committee.
Yeah. It was nice presentation.
Thank you, sir.
Next, Bhavan, I think Surya Reddy. Who is Surya Reddy? Is he here?
Yes. Hi, sir. Hi, sir.
Sir, is there any question?
Yeah. It is nice presentation. Don't worry.
Okay. Thank you, sir.
Right. Surya Reddy, actually, what is your number?
Sir, C10010.
I want to present my work, sir.
Yeah, you can. You can.
Sir, my number is B20. I am waiting
Sir.
since last 1 hour, 1.5
hours. What's your number?
B20, B120.
B1. Actually, in this, still we are at only A1. A129 only now.
Sir, can you present?
B120.
Okay.
Surya Reddy, what's your number?
Sir, C10010, sir.
Sir, I want to present my work A10029.
Wait,
sir.
Mohibul Khan, wait, please wait. Wait for this presentation. Mohibul Khan. Please, Surya Reddy, can you just tell me once again your number?
Sir, C10010, sir.
0010. C is not here actually with me.
Oh, okay, sir. Because
I'll make it here.
sorry, sir.
C10010 Surya Reddy.
Yes, sir.
Okay, we can start presenting. Make it only 5 minutes. Next, Mohibul Khan.
Sir, is my screen visible, sir?
Wait. Yeah, it's visible. You can.
Yeah. The full screen?
Yeah, so make it full screen.
Yeah. Is it visible, sir?
Yeah, yes.
Yeah, hi. Good afternoon, one and all. My name is D. Surya Reddy. I'm from Department of Physics, SP University. Today, I would like to present my work on electrical properties of AU, erbium oxide, N-type gallium nitride emerged with the erbium oxide insulating layer. As we come to the introduction, I choose gallium nitride as an semiconductor because it is the most promising semiconductor for the development of optoelectronics and microelectronic applications such as heterojunction field effect transistors, high electron mobility transistor, because it possesses excellent properties such as direct band gap and high background voltage and low on resistance. Generally, the Schottky diodes exhibits a leakage current and low barrier height.
Please concentrate on your
Okay.
main aim and results and discussion.
So the main aim of my presentation is to construct an MIS diode which shows better electrical properties than the Schottky diode. So that's why I choose rare earth oxide as an interlayer because it possesses high dielectric constant. And among the rare earth oxides, erbium oxide is one of the potential material which, because it possesses high dielectric constant, great conduction bandset and band gap. Because of this, I prepared AU erbium oxide and GaN MH diode with AR2 and correlate them with Schottky diode results. As we come to the experimental procedure, these NGAN samples were cleaned using ultrasonic agitation using trichloroethylene, acetylene, and methanol. And this for ohmic contacts, we used E-beam evaporation. For titanium, aluminum metals were deposited on NGAN surface, and for interlayer and Schottky contacts also E-beam evaporation has been done, and it was formed on NGAN surface. And the figure 1 shows the schematic diagram of the MS diode. As we come to the results and discussion, this slide shows the IV characteristics of Schottky diode and the MS diode. From this diode, we can say that the MS diode shows better rectification ratio and less leakage current as compared to the Schottky diode, which states that the electrical properties has been modified has been enhanced after insertion of an interlayer between the metal and the NGAN semiconductor, and higher barrier height and low ideality factor has been observed for the MS diode compared to the Schottky diode, which says that the AR203 layer significantly impacts the electrical properties. And as you come to the Cheng's method, this is the another method to calculate the barrier height and ideality factor from the nonlinear region of the IV characteristics. From this Cheng's method, the barrier height and ideality factor has been calculated, and the values are shown in this slide. And these values are very well nearly matched with the values of IV, which states that the device reliability and device reliability and comparison. As we come to the Naughty method, Naughty method is employed to calculate the barrier height and ideal series resistance from the forward bias, which states from the forward bias, and these values are shown in this slide. The interface state density of the Schottky diode and MS diode is shown in figure 5. As we can observe that the MS junction shows better lower interface states as compared to the MS diode, which states that the AR203 layer significantly pacifies the surface of NGAN surface and also efficiently reduces the interface states as compared to the Schottky diode. To understand the reverse current conduction mechanism under the reverse bias, log IR versus VR plot was been drawn, and this slope has been calculated, and the slope values matches to the theoretical values of Fuller-Frankel emission, and this states that for both the Schottky diode and MS diode, Fuller-Frankel emission is the dominant current conduction mechanism. As we come to the conclusions, MS diode, AU203 NGAN MS diode has been fabricated and compared the results for the Schottky diode. Better rectification nature with higher barrier height are observed for the MS diode compared to the Schottky diode, and the Cheng's and Naughty methods are applied. And these results are correlated with the IV characteristics, and based on these above findings, we can say that this diode is appropriate for the development of MIS and MOS devices. Thank you.
Okay, thank you. The presentation is very nice.
Yeah, thank you,
Then
sir.
now one question. Then you are doping with erbium. Okay.
Sorry, sir.
Studied about the luminescent property or something?
No, sir. Sir, I couldn't hear you actually clearly. What was the question?
Sorry.
Sorry, sir. Hello.
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 Yes, audible. You studied a luminescent property or something?
No, sir. For this, we don't study limiting properties.
Okay.
Okay, sir.
Then you can try. Okay.
Okay, sir. Thank you, sir.
Yeah, it was nice presentation. Next, Mohibul Khan. After Mohibul Khan, Arshia Ansari.
Sir, can I leave, sir?
Yeah, you can leave.
Okay, thanks, sir.
After Mohibul Khan, Arshia Ansari.
Hello, yes, sir.
Okay.
Yeah.
Okay, sir.
Sir, actually, I
Good
have two
afternoon,
papers
sir.
to
Yeah,
present.
you can bring
Hello.
First, let us finish this. Your presentation,
Okay,
30.
sir.
Next one, your one. Now, Mohibul Khan.
Okay, sir. Okay, sir.
Good afternoon. Today I am to present my work, optical characterization of nickel doped zinc oxide thin film. These are the outlines. These are the introduction. Already I have discussed previous. And these are the application. These applications do the further wide band gap for the optoelectronic devices like say solar cell, photovoltaic cells, photo detector, and zinc fluorescence also is for UV detector, gas sensing device, antibacterial coating, photocatalysis, light emitting diode, and drug delivery gas sensor, and etc. Experimental detail zinc and nickel doped zinc oxide thin film deposited by RF sparkling technique, where base pressure is used 3.35 into 10 to the minus 4 Pascal, working pressure set at 2.5 Pascal and 2.5 Pascal, and RF power set at 90 watt, and DC voltage set at 160 volt to 190 volt, and 220 volt for the 220 volt. Result and discussion in EDAX study, the elemental
Mohibul Khan, again your screen is stuck. Now it is okay. EDAX study.
EDAX, the elemental study of the debated film characterized by EDAX, where I have shared the two slides for 0 atomic percent nickel and 6.5 atomic percent nickel. X30 result of the deposited thin film showed that the deposited film is thin film is cubic hexagonal woodjet structure, which is confirmed by JCPDS file number 361445. The particle size of the also calculated by this method, and the particle size increases from 8 nanometer to 15 nanometer. Surface morphology characterized by atomic force microscope, where also the particle size also calculated by atomic force microscope. Particle size calculated by AFM, which increases from 7 to 19 nanometer. At the time of XRD, the particle size increases from 8 to 15 nanometer. Chemical composition of the deposited thin film characterized by Fourier transform infrared spectroscopy.
Mohibul Khan, just go to the conclusions.
Mohibul
Khan, go to the conclusions. Your screen is still stuck at the EDAX study only.
Okay, sir. The conclusion, the main conclusion of the work is that the particle size calculated from XRD, which is vary from 8 nanometer to 15 nanometer, with the increasing of atomic percentage of nickel from 0 to 6.5 8%, and the optical band gap energy also calculated, and which is the decreases from 3.17 electron volt to 2.23 electron volt, and the Arbas energy also increases 180 milli electron volt to 243 milli electron volt. This
Did you finish the
Thank you, sir.
presentation? I have a small doubt
Yes,
here.
sir.
I think you said say, at the end Urbach energy also calculated, right?
Hi, sir. I'm
Did you calculate
sorry,
the Urbach
band
energy
gap
or
energy
not?
calculated.
Band gap energy. So did you use the optical absorption spectra?
Yes, sir. I calculated
Okay.
band gap energy, sir.
What is the main importance of this band gap energy in
Optical
your work?
transmission spectra I have used.
Okay, Mohit, it's fine. Next participant, Arshia Ansari. Please present 30th 00030.
Hello. Yes, sir.
You just
Sir,
share
actually, I
your
have two papers to present, 0030
Actually,
and yes.
during this work, I have searched many previous work. Okay, thank you, sir. Sir, can I leave, sir? Hello.
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 You can please
you can continue. You just continue. Arshia Ansari. Mohibul Khan, your
I'm Mohibul Khan.
presentation
Can
is
I
done.
leave, sir?
Your presentation is done. You can.
Okay.
Yeah.
Thank
Arshia Ansari.
you.
Okay, sir. Okay, sir.
Yes.
Sir. Sir, is my screen visible?
No,
Hello?
yes, it's visible.
Okay, sir.
Okay.
Sir, actually, I have to mention that I have two papers to present. So one is 0030, another one is 0032. So should I do it consequently or wait for the second one? Hello? Hello?
Hello.
Yes,
Hello.
sir.
You can present this paper first.
Okay, sure, sir.
And after that.
Okay. Okay, sir. So good afternoon, everyone. I am Arshia Ansari from IIT Jodhpur, and the topic of my presentation is extraction of mono to few layers of graphene through micromechanical exfoliation of bulk graphite. So my content of the talk is introduction, then methodology and results and discussion, and then conclusion. So about the introduction, we know that graphite is an allotrope of carbon which exists naturally, and it has a layered structure. It is arranged, the carbon atoms are arranged in this in a hexagonal lattice. Now graphite has unique properties, but due to the weak van der Waals forces, it is hold different layers of graphite are held together by weak van der Waals forces. Also, it has exceptional electrical conductivity and high strength. But it has some limitations also, like it is very brittle and it has a high melting point around 3600 degrees Celsius, and it also has a conductivity which has an anisotropy. So it can be used for different electrical and electronic applications. So from graphite we can also obtain single to few layers of graphene, which is a two-dimensional material. Now graphene has excellent properties, like it is very strong, 200 times stronger than steel, and it is also very flexible in nature. Graphene is also transparent in nature, and that is why it can be used for touch screens and flexible electronics. It has 2D structure, it has very high surface to volume ratio, and it can be used for energy storage and sensors, different kind of biosensors, gas sensors, UV sensors, etc. And one property of graphene is that it has zero band gap. That is why it has very good electrical conductivity. So here in my this work we have successfully synthesized mono to few layers of graphene by using a simple scotch tape microexfoliation technique. So here in this figure the synthesis of the graphene is shown by microexfoliation method. So first we took a graphite crystal, which is a bulk form of graphite, and then we use stock scotch tape to to separate the layers of graphite onto the tape due to the pressure difference. And by doing this again and again and various iterations, we finally get few layers of graphene or maybe mono layer of graphenes, and that we deposit on the transfer on the silicon wafer from the tape. So here we have the results. As we can see, these are the optical images of graphene through various iterations. So now capital N is the first layer, or we can say it is the first layer of the graphene which we have obtained from the bulk graphite crystal. Then we do the repeated exfoliation of these layers. So by doing the 16 times, we get this kind of image. As we can see in A, and here we see that this graphene is not yet very thin because there is no transparency. So we again do exfoliation. Now by this we are getting a little bit transparent. As we do more and more iterations of exfoliation, the transparency increases. So finally there are different iterations, and we get by N by 264, we see there is a transparent layer of graphene by this optical image. Also, we have done the Raman spectroscopy for this layer, and we find out that it has a peak at 1328 centimeter, which is corresponding to the D band or the defect band, which is coming over here. So overall, this is a study where we have used a Scotch tape microexfoliation technique, which is a very simple and easy and cost-effective technique to use. And we have just broken the van der Waals forces that exist between different graphite layers, and we form the single or few layers of graphene. So we can say that these synthesized. Hello.
Yeah, just tell me.
You can continue.
Okay, sir. So this method is very simple and cost effective, and we can use this single layer of mono layer of or few layer of graphene for various applications, like as I mentioned before, like flexible electronics, transistors, gas sensor, photo sensors, biosensor, and different energy storage devices also. Thank you.
Okay, a nice presentation. Actually, are we prepared the graphene?
Sir, I have mentioned that we have actually purchased the bulk graphite crystal, and then use this Scotch tape method to separate the layers from a Scotch tape by applying the pressure.
Okay, applying the pressure. There is no use any other chemical or something like, only this Scotch tape technique.
We just use the Scotch tape. There is no, this is not a solvent technique, or we didn't use anything else, just the Scotch tape method.
Then please show the next image.
Sorry, sir. Hello.
The next slide. Please show the next slide.
Show the next slide. Yeah.
Yes, sir.
Yeah. Okay. This is an almond shape. Okay. Hello.
Yes, sir.
Okay.
Okay, sir. So, sir, may I?
Please wait for some time. Actually, let me finish next presenter.
Sure, sir.
Shahjad Ahmad. Shahjad Ahmad, are you ready?
Yes, sir.
Yeah, you start sharing your presentation.
Okay, sir.
If possible, 22 number, Bhavana HV also if study, please present after Shahjad Ahmad. Yeah, you start sharing, Shahjad Ahmad.
Sure, sir.
Number 22, Bhavana HV. If she is there, you can present after him. Shahjad Ahmad, please confine
Yes,
your.
sir. I'm just trying to share my screen.
Main aim and conclusion, results and discussions and conclusions of that your work.
Oh, sir. Sir, can you see my slides?
Yes. You can
Yes,
do
yes, yes.
Okay, sir. Sir. Okay, sir. So, hello, hello. Am I audible?
Yes. You can proceed.
Okay, okay, okay,
You
sir. Sir,
confine to main work only.
okay, sir. So, good morning, everyone. The topic of my presentation is alignment of SWCNTs through dielectrophoresis method, a potential FET device. Here's the content of my talk. First, I will start from the introduction, then it will be followed by methodology and experimental part, then results and discussion, and finally, the conclusion. So as we know, the nanomaterials, when we talk about the nanomaterials, we talk about when the size is below 100 nanometer, then we call it nanomaterial. So they have unique characteristics and behavior because they have high surface by volume ratio. So they have various different properties in terms of optical, electronic, and mechanicals. And here's the different form of carbon. The first form is graphene, a monolayer of carbon atoms that are organized in two-dimensional honeycomb-like structure. So we have different form of carbon. The first one is graphene, and then single-walled CNT, multi-wall CNT, and fullerene. Fullerene is a zero-dimensional structure of graphene, and SWCNT is the one-dimensional structure of graphene. Then the first about the methodology, what we have done here, we have used the n-type silicon wafer, and then we thermally oxidize it to create the oxide layer. And then the CNT-based field effect transistor was positioned on silicon SiO2 wafer. And then we have fabricated the source and drain electrodes uh, using the sputtering method. And here we use the gold as a source and drain electrode. Then here's the channel length is 5 micron, and then SWCNT uh, having the dimension, I mean the diameter is 20 to 50 nanometer, and we try to disperse in the solvent, that is the chloroform, and then we ultrasonicated to evenly distribution of the CNT in the solvent, and then drop cast it onto the wafer. And we applied the AC bias voltage by using the process dielectrophoresis. And so there's a peak to peak voltage that is 8 volt, and the frequency 1 megahertz. And then wafer was treated at 100 degrees centigrade to remove the unwanted solvent. So here's the structure. You see, this is a schematic of the device, and then this is in the B. The figure number B shows the SEM image. You see there is a CNT between the source and drain, and the size of the CNT here, the length. I mean, it's about 5 to 10 micron. Yes, and here's the IV characteristics. It show the nearly ohmic character 8 volt and 12 volt. And here's the conclusion. So we can use this kind of device in making the potential biosensors, and it holds a promising, considerable promise for the transmotive advancement in the biomedical domain. And it also holds the potential to be utilized in real-time monitoring of the diseases or any biohazardous molecule. And so we can prevent the potential hazardous things for the human beings. So thank you very much.
Shahzad, can you just show me the figures which you have displayed earlier?
Here?
Yeah.
Yes, sir.
So in this experiment, we presented SEM and VI characteristics of the
Yes, sir.
material, right? So you are
Yes, sir.
confirming through the SEM as this small walled
Single wall.
single wall, sorry, single
Yes,
wall
sir.
CNT. So did
Yes,
you
sir.
try this SEM nanostructure with the TEM any?
No, sir. Actually, we don't have any facility uh, to do the characterization for them. Yeah. So we just tried
Okay.
with the SEM. Yes, that's fine.
I think there is one more presentation from your Sajad Ahmad in
Yes,
this,
sir.
right?
Yes, sir. Yes, sir. Yes, sir.
Okay,
The
let us
percentage is
first.
0033.
Yeah, let us wait for Kalidas Gaikwad. If she is there, Kalidas
Okay,
Gaikwad,
sir.
you can leave.
Okay,
Kalidas
sir. Sure.
Gaikwad. Kalidas Gaikwad.
Yes, sir.